Hello, my dear students. In the last class, I discussed about how to draw SFT and BMD for the different types of beams with the different types of loading. Today, I will be discussing about how to draw a loading diagram from shear force diagram. Okay, till now you have calculated or drawn SFT and BMD from the loading diagram. This is slightly different. From the shear force diagram, you have to draw a load diagram. Then bending moment calculation is same. Okay. Sometimes instead of load diagram, a shear force diagram for the beam is given. In such cases, we first draw the actual load diagram and then the bending moment diagram. The load diagram for the beam may be easily drawn by keeping the following points in the view. So there are some just tips how to draw the loading diagram from the shear force diagram. The first one is if there is a sudden increase or decrease, that means vertical line of the shear force diagram. It indicates that there is either a point load or reaction. That means reaction means support at that point. Okay, means if there is a sudden increase or a decrease of the vertical line of the shear force diagram, it indicates that there is a point load or there is a reaction. Support. Okay, at that point. Suppose if there is no increase or decrease in shear force diagram between any two points, that means the shear force line is horizontal and consists of rectangle, it indicates that there is no loading between the 2 points. If there is a line is horizontal and it consists of a rectangle, it shows that there is no loading between the 2 points. This you think, now you have drawn many shear force diagram from the loading diagram, right? So next point is if the shear force line is an inclined straight line between any two points, it indicates that there is a uniformly distributed load between the 2 points, correct? If there is a straight inclined line, then you obviously know there is one uniform load between the 2 points. Next point is, if the shear force line is a parabolic curve between any two points, it indicates that there is a uniformly varying load between the 2 points. If that shear force line is a parabolic curve, then it indicates that there is an uniformly varying load is acting between the 2 points. Once after drawing the load diagram for the beam, the bending moment diagram may be drawn as usual. Once if you get that loading diagram, you can calculate the bending diagram. Okay, so these 4 points you have to remember while converting shear force diagram to load diagram. Okay, let us take one example. A figure shows the shear force diagram of a loaded beam. Find the loading on the beam and draw the bending moment diagram and indicate the position and magnitude of the maximum bending moment. Okay, this is the diagram given. Okay, see here, this is one A, this is A, B and C, D. See here, there is a straight inclined line, means what? There is a UDL. Here also there is inclined line. That means straight inclined line means there is a UDL, and this is means what? Rectangle means there is one vertical force or support at this point. Okay, so we will find. You can directly draw if you are so thoroughly with the concept, no problem. Otherwise, I will do step by step. Okay, what you can do, see at a suppose I start from here. At A, we can see that the shear force increases suddenly from 0 to 10 kilonewton. You can see here at A it is 0 and it increases to 10 kilonewton at A, right? Means there is a support reaction of 10 kilonewton at A. Here there must be one support reaction of 10 kilonewton at A, and that is we are starting from this side now, left side upward is positive, so there must be a support reaction of 10 kilonewton at A, this point. Okay, next between A and B, this point here between A and B, the shear force diagram has an inclined straight line. You can see here inclined straight line between A and B. Therefore, The beam is carrying a uniformly distributed load between A and B. This means that there is an UDL is acting between A and B. And also we can see that there is a decrease of 10 to 5.5. Here this is 10, decrease of 5.5. So how you can calculate 10 minus 5.5, that is equal to 4.5. Okay, for a length of 6 meter, UDL is what? Always load multiplied by the distance, right? So here 4.5 is there kilonewton, and it is for a 6 meter length. So how you have to calculate uniformly distributed load? 4.5 divided by 6. This is the length. Okay, that gives 0.75 kilonewton per meter. So that is the UDL. Why this is divided by 6? Because see, this is kilonewton, right? This is kilonewton. You have to convert into intensity. UDL is always kilonewton per meter. So you have to divide it by 6 per meter. Okay, so divided by 6. Once if you divide it by 6, you get 0.75 kilonewton per meter. When actual diagram, in the loading diagram, it would be like this, 0.75 kilonewton per meter. Then what you do, you multiply it by the distance, then it becomes 4.5, like that. Okay, here you have to, this is the load, so you have to convert into intensity. So therefore it is divided by 6, okay, length. So you get 0.75 kilonewton per meter. Next, at B, here you can see that there is a sudden decrease of 5.5 to 1.5 here. You can see there is a decrease of 5.5 to 1.5. But this 5.5, that is a plus, right? And this is minus 1.5. So 5.5 minus of 1.5, there is a sudden decrease. So that is 5.5 plus 1.5, that becomes 7. Okay. So thus there is a point load of 7 kilonewton at B. So there must be a point load of 7 kilonewton at B. That is the meaning. Then at between B and C here, between B and C, there is a an inclined straight line, and therefore the beam is carrying a uniformly distributed load between B and C. Right, here there is again inclined line. There is you have to understand, you have to think that there is one uniformly distributed load is in between B and C. How we can, there is also decrease of 9 to 1.5. Can see here this is 9, here it is 1.5. So 9 minus 1.5, that is 7.5, and in a length of 10 meter. Again this is intensity, load, here it is load, you have to convert into intensity. So divided by the length. The length is 10 meters. So this is divided by 10. 7.5 divided by 10, that is equal to 0.75 kilonewton per meter. So means that again here there is one UDL of 0.75 kilonewton per meter for a distance of 10 meter. Then what you can see at C, it is here again you can see that there is a sudden increase of 3 kilonewton here. That is because see here it is 9, it increases, this is minus, right? It increases to plus 3. Okay, so what is that? So 9 plus 3, that becomes 12. So total it is 12. Thus there is a support reaction of 12 kilonewton at C. Between C and D, the shear force diagram has a straight horizontal line. You can see here there is a straight horizontal line. So means between C and D there is no load is acting. Then at D it is again decreased to 0, right? So means that there is a point load of 3 kilonewton at D, right? So that is the meaning of because shear force at that point is decreases to 0, 3 kilonewtons is 0. That means there is a point load of 3 kilonewton at B. Now we will draw the diagram. So this is the shear force diagram. From the shear force diagram, you have to draw the loading diagram. How it is at A, it is 10 kilonewton load, and between A and B, there is a UDL of 0.75 kilonewton per meter for a length of 6 meter. Then at B, there is a point load of 7 kilonewton here. There is a point load of 7 kilonewton at B. So that you have to write here point load of 7 kilonewton per meter kilonewton. Then again there is one UDL because here there is inclined line. So that is again 0.75, 9 minus 1.5 divided by 10, 0.75 kilonewton per meter. Then again here it is increases to 3 plus 3. So if you put 12 here, then you get that is 3 here. So there is a point support reaction of 12 kilonewton. Then again it is decreases to 0, means at D there is a load of 3 kilonewton which is acting at D. Okay, so like this you can draw loading diagram. Then simple thing, bending moment diagram, that you can do as usual method. At D it is 0 and at C it is minus 3 into 2 and minus 6. Then at next point is B here, that is 3 into minus 3 into 12 plus 12 into 10 plus 0.7 minus 0.75 into 10 into 5. You get 46.5. Then at A, obviously you have to get 0, but still you do that. 3 minus 3 into full length, that is 12 plus 6, 18. Then this is plus, moving like this direction, plus 12 into 16. Then again UDL minus 0.75 into 10 into half of 10 is 5 plus 6 till A. So 5 plus 6 minus 7 into 6, this distance, minus 0.75. Again this is UDL of 0.75 into 6 into half of 6, 3 equal to 0. Then draw the bending moment diagram. Okay, as usual method. At D it is 0. At C it is minus 6. So it is below the line. Then here it is it was calculated at every point. Here it is not required. You just find what is the next point at B, that is 46.5, and at A 0. So draw this. So where will be the maximum bending moment here? Where the shear force changes its sign, there will be maximum bending moment. Here shear force sign changes at the point here, bending moment, negative bending moment here, that occurs at this point. Okay, positive bending moment also there. Here 2 points you can see the bending moment changes its sign at C and at B. At B it is plus 46.5. At C it is minus, that is minus 6 kilonewton per meter. Okay, like this you can calculate what is how to draw loading diagram from the shear force diagram. I hope all of you understood. We'll discuss one more example in the next lecture. Thank you.